Okay, happy Monday, everybody. Welcome to your first bit of bonus content for Eng 1500 throughout your mid-semester recess. So throughout actually the rest of the semester, I'm going to periodically produce additional videos that I can throw up for you, which contain content that's not necessarily strictly related to a learning objective of 1500, but it is something that I believe is very important or useful for you to know as engineers. So today we're going to be talking about engineering drawing, which is something that cuts across virtually every different field of engineering in some way, shape, or form. We use it to communicate with each other. So it's something that I think is going to help a whole bunch of you to know more about, especially those of you who are currently doing design and build or very much just design projects now. This is going to be super useful to you, right? So that's the idea of any bonus content you see go up on the channel at any stage. So as always, as I love to talk about in 1500, communication methods are a thing that we focus on massively. We spent forever talking about written communication skills, which is drastically important. In week 8-ish, depending on where it now fits in our new semester, we'll talk a bit about presentation skills as well, and I'll teach you some tips and tricks around how to give good presentations. And intrinsic to both good writing and good oral communication skills, we'll talk about visual communication, right? We talk about it whenever we can using these things in combination with each other. And some of this we've been over. Using figures to communicate complex or visual-based information is just fundamentally important to engineering. A lot of times I like the logic of show, don't tell. So kind of in my head, when I need to communicate something, I'd never write something down that I could say to someone because I lose communication effectiveness. So speak instead of say, and then whenever I can, show instead of tell. If I can give you a figure or a picture to represent something, I'd much rather do that than try to explain it to you. So if you can have a similar logic, show, don't tell whenever possible, that'll really enhance your communication skills. Because so many things in engineering, they're either so much easier to just communicate by going, hold on, I'll just draw it for you, there it is. Or sometimes the only way to communicate them is visually. The example being, describe the color blue. It cannot be done. So sometimes visual communication is all you have. So it's super useful. What we haven't really spoken about as a visual communication method yet, though, is engineering drawing. We sort of danced around it a little bit, but there is a particular way in which engineers draw things to communicate. So just like, technical writing was its own form of written communication, engineering drawing is its own form of drawing to help us communicate. So what I'm going to cover today is not comprehensive by any means. It's a crash course, short, sharp introduction to this stuff. It's big. The first course I ever got the pleasure to teach was actually the course Mech 1110, which all mechanicals, mechatronics, and a bunch of medical engineers and all the aeros all take, with a focus on 3D modeling and technical sketching is basically what makes up a huge part of that course. So I did get to use to teach this, and I'm going to give a brief overview of that, but I also want to highlight that although I'm going to use some small examples in this, the concepts behind engineering drawing really transcend a whole bunch of the disciplines themselves. So if you look at things like schematics, for example, which are a type of engineering drawing very commonly seen in electrical engineering, right? If you go on the big scale, you're going to see building plans and things like that, which is obviously throughout civil surveying engineering. And then you can go even bigger again, and you get to things like topographical maps where your surveyors and your enviros are kicking in, but it's all just different forms of engineering drawing. So, crash course. Tech drawing is a thing that some of you may have seen or heard about before. You may have done something like this. This is what I did in school when I did tech drawing. Whole bunch of different pens and paces and mechanical pencils and set squares and everything like that. Totally dead field. Hey, nobody ever. This doesn't exist anymore. This isn't what a drafts person is the term that we'd use for this person. Drafts people don't do this. They do this. Nowadays, it's 3D modeling. The old school tech drawing style, it's just dead. So there are some skills, if you did learn that stuff, that will be applicable to you, like line styles and things like that. But nowadays, there's a totally different logic that exists to drawing. And what you do when you're doing 3D modeling is you actually make a 3D model first, and then a drawing kind of falls out as a result. So making drawings is actually really quick if you do it well. So the way that it works now is you kind of sit in one of two camps. When you want to draw something, you either sketch it freehand on a piece of paper, or you go and you make a full-blown 3D model. And there's no real reason to ever basically draw a line with a ruler ever again in this field. It doesn't exist. If you're going to bother to get a ruler out, go and make a 3D model and make a proper drawing. So here are two different drawings of our object that we showed before, our running example. And you see up the top, that's a freehand sketch that was done entirely by hand and then photo taken and scanned in. And then down the bottom is the 3D model version of that same drawing, right? So this is it, either there or there, one or the other. All right, so what I might do very quickly is I'll show you how I made that model. And the reason I want to show you this is because I want to show you the glorious benefit of making a 3D model rather than just straight up making a drawing. So this program is called Creo. It's a parametric modeling program. It's the one that we use here at the university. If you want, you can find a link to download it in the folder, the Red Bull folder. Has a link to it. And there's a bunch of videos that were made by Dr. Sam Evans on YouTube if you search for Mech 1110, and he made a whole bunch of tutorials to teach you how to use it. You definitely don't need to use it to do this course in any way, shape, or form. But it's something that if you've got an interest and you want to learn how to do this type of stuff, you can. Creo is really good. It's incredibly powerful. It's also incredibly expensive, but you don't pay for it, so who cares? It's actually their business model, basically, is that they give it to students and universities for free, such that when you graduate, you know how to use their program, and then they hope that means that your boss buys the very expensive version of this. Where is my sketch? 7 from the bottom. Okay. Okay, so I just made a model of this thing. Great success. Awesome. So that's our object that we had. That's what our sketches implied, by the way. So I've made that. What you can do here in most packages, they all work slightly differently, but they all work kind of the same. I want to make a new drawing. So I made a part originally. I want to make a drawing now. I'm not going to use the default template because it sucks. Empty, A4 page, whatever. It's not the point of my story. Get out of my life. Cool. Yeah. I'll turn my axes off because we don't need them. So here's our thing. You probably want some dimensions on that. Show model dimensions. Yeah, just show me all of them. Whatever. I'm assuming they're fine. And we have a model. So fully dimensioned, nicely set up model here. I'll just move some things out of the way because why did you give me that as 32? It's not useful. Would be much more useful would be to have that dimension. All right, whatever, you can go there if you want to go there. Yeah, so we can make a drawing up like that. As I said, once you've got the 3D model, making the drawings trivial. But what I want to show you here is the real advantage to having a proper 3D model that's made in a nice, robust way, is if I come back to my original sketch here and somebody says, no, Dylan, we messed up. These were meant to be 12 mil holes, and this thing was meant to be 101 millimeters wide. Okay. Bang, bang, changed. And if I go back to my drawing, hey, look, it's automatically updated this information for me. So where this becomes super useful is in the revisions of drawing. So as you go through it and you're constantly iterating and making your design better and better and better, you end up with everything kind of updating and changing together. And you can force things in this model to make it be, as you may not have noticed, that I force these things to be symmetric. So regardless of how big I make this, these things will always stay symmetric around. And you can force stuff like that. So that's really, really nice. And there's some places, and I know one of the people who makes the F-35 has banned paper drawings in their workshop. So because they're constantly making little tweaks and little updates to them, they want to make sure everybody always has the latest version. So if one person makes a change, they just all access the same shared file, and nobody ever prints anything, so nothing is ever outdated. So it's amazing if you can make good, robust models. So that's kind of the real value of doing 3D modeling. You can also use it to do things like, once you've got this model, you don't often need a drawing anymore. You can just send that straight to a CNC machine or a 3D printer or whatever, and you can produce things without ever even making a drawing anymore, which is another reason why it is dying as a field, the whole drawing thing. Cool. So huge benefits to knowing how to 3D model. The issue with it is it's often quite a slow practice. So that's a fairly trivial example, but in reality, if you were to sit down cold and you were to try to make a 3D model of this and then a drawing, it'd take you 10, 15, 20 minutes probably. I've built that once or twice before. However, to do a sketch like this probably takes you 2 minutes. You're looking at maybe a tenth of the time to just make a sketch up of something like this. So this is often much faster than the whole 3D modeling, although the whole 3D modeling is more robust. So there's trade-offs between which one you're going to do. The other thing that is really important to know, though, is I'd virtually never try and make a complex 3D model without first making a sketch of something anyway, because the first time I made this object, I was constantly referring back to this sketch to get what all the dimensions were. And you notice I had to go back and I had to check that this was 7. So with the rise of 3D modeling, the importance of 2D quick hand sketching has actually become more and more important as well. Which is not the way that most people think about it, which is why I kind of labored in that point for a little while. Alright, so if we're going to learn to do a bunch of this sketching, what we want to be thinking through is, what are our overall goals? What are we trying to achieve by doing this thing? So predominantly we need to remember that this is a communication method. So our job is to take an idea that we have in our head and we have to put it in the head of whoever our audience is. If we're capable of doing that, then we're doing well. If we're not capable of doing that, then we're not. And this is going to become quite important about where we do need detail and where we don't need detail or accuracy or whatever. Very important, we're not making art, okay? So just because somebody can take a ballpoint pen and draw that, and oh my god, that just blows my mind that somebody is that gifted to be able to do that, that's incredible. Yeah, it's super not what we're talking about today, okay? We're talking about the ability to communicate information. So what's up the top communicates a huge amount of information to me. What's down the bottom impresses me, but doesn't teach me anything, okay? So we're not looking for artists here, and just because you're a terrible artistic drawer doesn't necessarily make any difference. In the same way that you might have been a good or a bad creative writer doesn't affect your ability to be a good or a bad technical writer in any way. So most often we're communicating with other people through our drawings. We've kind of spoken about this, a picture saying 1,000 words. This on the right here is actually my favorite example of the benefits of a quick technical drawing. This was done by a guy who was in a foreign country working with somebody and they didn't speak the same language. So guys on a business trip or whatever, I don't remember the full backstory, working with somebody, didn't speak their language, made this drawing, handed it to the person, done, not a problem. Universal communication. So it can entirely replace all the words that you need to share with somebody if you know how to make an appropriate drawing. Another good thing to communicate between, so obviously engineers and tradespeople or engineers and other engineers do this all the time. Past and future you might do this a lot as well. I do this for myself loads. Draw something up, put it down, come back to it 2 weeks later, kind of forget all the nitty-gritty details. Oh, hey, all good, they're in the drawing. So particularly when you're working on something complicated that might have hundreds and hundreds of parts to it, you don't want to have to try to keep all of that in your head at any one stage. You make drawings for yourself. I cover my whiteboards in drawings all the friggin' time. And you can certainly put this type of stuff in a report. That is more than acceptable to go into an engineering report in 1500 certainly, but even into like an honours level engineering report, that would be perfectly acceptable. So between you and a marker, you can communicate through a sketch as well. As always, formatting rules, because formatting rules are the best. We're going to talk about these for a little while a bit later on in this presentation. Whole bunch of formatting rules when it comes to engineering drawings around things like line styles. So as of just a one-off quick one, this long, short type of line here, this is what we call a center line, and it denotes to me that that's the center of a circle. So even though this guy maybe didn't draw a perfect circle freehand, he gave me center lines, I know what's going on, that makes sense to me. So there's all these rules around how you format things that help you communicate information, which is generally our #1 goal, right? And it's how it helps us not have to be artistically brilliant if we use the formatting to help us. The other side of technical sketching might actually be not as a communication method at all, but as a thought process method for you. So when you're trying to design something and you're sitting there imagining it in your head going, oh yeah, this would slot into here and this would connect to this and I'll wire this thing here and then this will light up and da-da-da-da-da. It probably all works in your imagination. But it's not until you can actually start to draw that up on paper and go, oh, but that would actually mean that this bit of metal and that bit of metal would cross straight through the middle of each other. Oh, that's not going to work. So basically my kind of logic is until you've made a drawing of it, it's not a design. It's a bullshit idea in your head. It's nothing. And until you can actually draw it on a piece of paper, put dimensions on that drawing and give it numbers, it's worthless, okay? So it doesn't, again, have to be beautiful. It has to be effective. So, but it can really, really help in your design process. Cool. So these are overall goals that we might want to get out, and just kind of keeping those in our head does keep us remembering why we're doing this thing in the first place. And that's sort of the next really big important point. Whenever you are drawing anything, in fact, whenever you're designing anything in general, and then as a result when you're drawing it, it's really important to have a very clear idea in your head of what that thing's purpose is in life. Why has it been summoned into creation? And this is a bit of an example. This is the same object, dimensioned in 3 different ways. If you sent this to a 3D printer or a CNC, you'd get exactly the same object back every time. What is interesting though is that these 3 different ways of dimensioning it actually imply to me that this object has 3 totally different purposes in life. And I'm going to actually circle back to this slide. So I'm going to go and do another slide, and then I'm going to come back to it and we're going to talk about it again, because I think it'll make more sense in a minute. I'm going to first talk about tolerances. So some of you may have heard this, some of you may not. This object was supposed to be 74 millimeters wide. The tolerance that we talk about is how accurate. 74 millimeters is 74.5 millimeters good enough? Is 74.1 millimeters good enough? Like, what do you want to measure this down to the atom to check that it's perfectly 74 the whole way across? Like, how accurate do you need to be? If you gave me a chunk of steel and said, cut me off a piece 74 millimeters wide, and you gave me a hacksaw, if I could get it somewhere between 72 and 76, I'd probably be proud of myself. That's not my skill set. Would have that been acceptable in this object? If you instead gave me a milling machine and an hour or so to set myself up and do it properly, I'd probably get you 74 within plus or minus 0.25 on the crappy mill that we've got in our workshop. If you went and gave it to somebody who was actually, good at what they did, a tradesperson would get you 10 times better than what I could get you with a nice machine. But this is just a rabbit hole. Okay, this just keeps going, and you get to the point where you're looking at highly precise machining on things, and people are actually having to calculate that when you machine, you heat the object up, and it thermally expands as a result of that, and then you cut through the thermally expanded material, and then it shrinks when it cools back down, and you end up with cuts that are slightly bigger than you expected them to be. And so you're having to compensate for that type of thermal expansion to get that tighter tolerance. And it's turtles all the way down. It just keeps on going. And sometimes it matters, and most of the time it doesn't. So there's been, on occasion, I once asked a tradesman to take a piece of 32 millimeter tool steel and cut a groove into the front face of it, cut a depression into the whole front face of it that was exactly 50 microns deep to the best of their ability. We were having to compensate here for things like the point of the tool itself bending out of the way as it was trying to cut and stuff like that. And we got within, I think Dean, I didn't contribute to this at all. I think Dean got it to 42 microns deep, and then we were like, yep, that's good enough. That took 7 hours, I think, and my piece of steel is now cost me like $1,000, roughly $1,000 to get that made. So that's where this becomes really important. I turned what was like 10 cents worth of steel into something that cost me $10,000 for paying tradesmen time and tool setup and stuff. In order to $1,000, to get something because I put a stupidly high tolerance on it. Now I needed it, and I was happy to pay that much for that object. But if I'm outside building a rabbit hutch, am I going to be doing that? Or am I going to be using the absolute coarsest tolerance imaginable? And that's actually what you want to do as an engineer. A lot of people get caught thinking, oh yeah, I want to make this as nice and as shiny and as perfect as possible. And you are just pissing money away doing that. What you want to be thinking is, what's this thing's job in life, and how quickly, roughly, coarsely can I make it before it affects how useful it is? So what's its job? Doesn't matter. Doesn't matter if when I cut this piece of wood for my rabbit hutch, it's got an extra 2 mils hanging out one end. Probably not. So cut it quickly, move on with your life. You can use those resources to do something else better later. So one of these tolerance things is generally around how well you can machine something to be the right size. But another one's often around what can you physically purchase. So let's assume I'm designing my rabbit hutch and I want to make it out of bits of wood that are 20 millimeters wide. I don't know, 20 by 40 mil wide is what I've designed for. So I go to Bunnings and I go, can I have some wood that's 20 by 40? And they go, no, we don't sell that. We sell 19 by 42. Is that okay? They sell, thicker stuff. Do I need to go and buy this thicker stuff and cut it down to be exactly 40 by 20 and cost myself some huge amount of money? Or am I willing to accept this other piece of wood? So having that good understanding, because you're going to exist in this space all the time. I can only get set sizes of things. So you're going to really want to understand that well early. Is that 1 or 2 mil difference important in your tolerances? The other thing to know is when it says it's 42 by 19 by 1.2 meters, how accurate is that? Is there a tolerance on those numbers? And anybody who did the D-cell project, chemical or renewable engineering, should have noticed that no bits of wood that you buy from Bunnings that say they're 1.2 meters long are actually 1.2 meters long. They're all different. They're all different. So, with this in mind, let's go back to our object. This thing was supposed to be 74 mil wide, right? Now let's assume that the material that we purchased wasn't 74 mils wide. It was 75. Now, this is where our design intent starts to make a big difference. So that goes from 74 to 75. What happens to this drawing? Well, in this case, these two holes stay 40 millimeters apart and they stay symmetric. And that dimension there and that dimension there change to become 17.5. Okay? Not here though. In this drawing, it stays symmetric still, but that stays at 17, that stays at 17. So that becomes 41, and those holes actually get further apart when that becomes 75. Okay? And in this case, that becomes 75, stays at 17, stays at 40, that becomes 18. This object is no longer symmetric. So, which one of these is acceptable? This entirely then depends on what this object's application is in life, right? So, if there's already two pins sitting somewhere 40 mils apart, and it has to slide over the top of them, then that's not acceptable anymore. That might be, well, both of them are, but that one's not. But maybe it needs to be symmetric. Maybe this one's no longer acceptable. You really want to understand and you want to try to capture with your drawing what the purpose of this is. Because when I look at a drawing like this, it implies a whole lot more to me because of the way the dimensions are put on it than maybe you thought about when you first put them on. Cool. So that's basically the design intent part of it, and something you want to constantly keep in your head. Similar little bit of a side shoot, but in the same way that putting really high tolerances on things costs you huge amounts of money, putting really high what we call surface finishes costs you money too. So an example might be if you go and just get a piece of wood and you cut through it with an axe, it's probably got a terrible surface finish, all jagged. A saw is probably a bit better. If you then got it and you filed it, it would get better again, and then you could sand it with progressively finer bits of sandpaper and improve the surface finish each time, right? But every time you do that, you cost time, which means you cost money, you cost resources. So what's the worst acceptable surface finish is generally, again, the one you want to go with because that saves you resources to spend where they're more important. These are just two traps for young engineers that fall into them all the time, speccing stupidly high tolerances and stupidly high surface finishes. Cool. All right. So that's a bunch of the background information that we wanted to think about. When it comes to actually getting out a piece of paper and a pencil and drawing something, let's go through a bit of a strategy on how we might want to do that. So just like all our other communication methods, we're going to go through a planning, which was kind of that whole design intent stage, and then a draft and revise stage. Sound familiar? Yeah. So the nice thing about doing sketches is they're cheap. They're fast and they're cheap. You generally, for an object like the one we're talking about, you're going to spend 2, 3, maybe 5 minutes on a sketch. Which means if you get 90% of the way through it and you realize no, I started in the wrong spot, this is bad, throw it in the bin, start again. It was 5 minutes. Just throw it in the bin, start again, do it again until you get it right. Don't be afraid to do that. Don't go back and try to fix too many things in a sketch. Just start again. Trust me, it's faster. Okay, so a strategy for actually drawing something. It's like I don't know, a series of steps here that I'll take you through. This is how I draw it. This is certainly not the only way to draw. And if you're very good at doing this already, go nuts. Ignore what I'm going to tell you. If drawing is something that you find really hard, and I found this horribly difficult when I started, these were some of the steps that I would go through. So the first thing that I would do is draw it very, very lightly to begin with. And so that was my piece of paper. I sketched this out. I had a 2B pencil, so it's quite a black pencil, but I just dragged it around really, really lightly to sketch it out. It's not great. It's not particularly square. It's not particularly good anywhere, but it's basically just giving me a rough skeleton to start with. I am fully aware that I'm going to come back and go over this again later, so I'm not stressed about it. I also started with a big base-like object that I could then hang all my other geometry off. Fairly obvious in this example, but it was just like this big square, well, big rectangular plate in the beginning. And then I came and I started to dangle other bits of geometry from it. So I didn't try and draw the circle first, or try and draw this bit and then this bit and then this bit. I just drew the big square box. Because once I had that, I could put all my other geometry inside of it, right? So I had my big rectangle, I put my other things in, and I actually hung my other view, which is going to appear down here, off the box. So I did what I would call projecting another view. I continued this line down, and I continued this line down to help me create the area in which my next view is going to go. Again, I draw a box. So if we remember this object, it's got to be cut out in the middle of it here. I didn't come along with my pencil and just try to one-shot this and draw the big curved cutout. That seems difficult to me. That's hard. So I just drew a box. And then I'm going to actually draw another box inside of this. So I projected these lines down, and I drew myself another box. Now, I know that my complex geometry is going to go inside of here. I haven't, again, tried to draw it yet, but I've contained it to where it needs to go. Same deal, I tried to project my holes down. They were a bit trickier, but, you know, they're there. Then I come in and I drew my more complex geometry. Pretty badly, but the nice thing is even if I don't draw a great curve here, it's going to remain roughly the right size and roughly the right shape, provided I keep it within the lines that I've drawn for myself. So this is how you can help yourself as much as possible. And the more complex your object becomes, you still just start with a big box. And then you draw sub-boxes inside of that. And if you have to, sub-boxes inside of that again. And then you can just join up the bits of geometry. That makes way easier to draw, okay? It keeps everything the right size. It keeps everything proportional and roughly correct. All right, then I just come through heavy-handed and I reinforced all of my exterior lines. So in some cases when I was happy with my light lines, I can effectively just trace them. But in some areas where my light lines are a bit shitty like they were up here, I tried and square my box up a little bit. You can see my holes were pretty average to begin with, and I made them slightly better. What you're trying to do here is make sure that you've got some contrast. So it's now very obvious that this is an outline and this is a leader line. It's important. Then I came in and I added details and then dimensions. So I've dumped some center lines in here, some hidden lines to represent my holes. And then I went and dimensioned it. So this would then be, I'd be okay with this. I would very happily walk into a workshop armed with just this drawing and be able to start making, or open up my solids modeling package and make this object as a result of this sketch. Meaning it achieved its goals, right? So it may not be pretty, may not be a work of art that's getting hung on the fridge by your parents, but it's effective, it does its job. If you realize that it was not doing its job, that whole thing, including taking all of those photos, took me about 6 minutes. So throw it in the bin and start again. Who cares? They're cheap. And you do get better with practice. You do. So Yes, your first one will probably be pretty dodgy. That's fine. Just keep iterating at this. It's a skill like every other skill. You get better at practice. Sucking at something is the first step to becoming kind of good at it. So get in, have a go. You'll get that. That's fine. All right. Cool. So we've drawn our thing up. And there is an extra, I guess, sub-underlying set of assumptions that we haven't spoken about yet that are going to make this whole communication process way easier for you. And they're all kind of based around only giving a limited set of information so that the user then assumes everything else. So basically what I mean is, as a reader of a drawing, it's on you to make the assumption that things that look straight are straight, things that look round are round, or centered, or equal, or aligned. And unless the drawing explicitly states otherwise, then that's what you assume, okay? So, for example, this top line, it's not perfectly straight, right? It kind of narrows in a little bit, and that dimension is probably actually slightly smaller than that dimension is. But because it's not labeled, my assumption is that it's 30 on both sides and that was meant to be a straight line. Same deal for the circles. They're not labeled as anything other than circles, so I'm just going to assume that they are. So what becomes really important when you are reading and also drawing something up is what you don't tell somebody is just as important as what you do tell them. So absolutely everything you put on a drawing has a purpose, and everything you leave off a drawing has a purpose. Otherwise, we just make all of the assumptions, all right? So it's kind of interesting that this 15 dimension, for example, is there, as is that 30. If that wasn't there, they didn't bother to label that as 15, I would have looked at this and seen these holes that are roughly centered and this 30 dimension, and I would have just made the assumption that this was supposed to be 15. And I don't actually need that dimension. It being there tells me that centered isn't what this person is going for. It tells me that they're going for 15 from that edge and then 30. But maybe if this became a 31, this would stay at 15. It wouldn't be centered, because they implied that by putting on two sets of dimensions. So you can actually get this information across with much less than is here. So never use a useless dimension. Never dimension something twice that shouldn't be dimensioned twice, because you imply something different to your reader. Same deal in terms of views. And we are going to talk about the views again in 1 or 2 slides time. But you can see 2 views of this object. Both of these views are needed. No other view is required. And if you put in a view that another view, it would imply to me as a reader that there is a very good reason this is here. So there must be some part of this that required an extra view. So never use a redundant view if you don't need it. It creates confusion. It doesn't help. All right. The one exception is what we call reference dimensions. So this drawing is actually double dimensioned. And if we were to roll back out of interest inside of a program, a 3D modeling program like Creo, it won't let you dimension something twice. If you try and dimension it twice, it will throw an error and say you're doing it wrong. You get 1 dimension for this thing. Just so you know. All right. Let's assume I've got some random plate and it needs to go on to some other part that already exists that's got these 3 pins that come out of it. So I just need these 3 holes. The problem is I go on and measure these pins up and they're these weird distances apart. It's at some weird angle. It's really hard when you're in a workshop to work with angles. Angles are horrible things to work with. Protractors are horribly inaccurate pieces of equipment. So we never work with angles if we can ever avoid it. By far the best thing to give a tradesperson is a series of Cartesian or linear dimensions. So exactly this many millimeters from a nice corner that they can put a ruler on and they can mark. So that's the easiest way for them to get the locations of these 3 holes. These dimensions in brackets are dimensions that I'm saying aren't required to build this object, but it might be a useful thing for you to know. So basically, I've done some maths for you, and once you mark these 3 things out, if you put your ruler from there to there, it should read exactly 100 millimeters. And if it doesn't, maybe we've got some errors somewhere and we need to go back and fix them up. So reference dimensions are just a check, basically. They're not to be used to build the object. They're just a check at the end, and you put them in brackets. Other than that, no redundant dimensions, because there is no such thing. Cool. So on top of those assumptions, there's then a bunch of different symbols and line styles. So these are a bunch of formatting, almost grammar rules that you have when you're doing drawings that you can use to communicate more information. So we've seen a bunch of these already, and there are heaps of them. So if you go back to the old school tech drawing sets, you would have, if anybody ever did it, maybe got several different mechanical pencils with different thickness leads in it. And then it's different styles of pens with different tips as well for inking in different lines and all sorts of stuff. And I'm not going to hit you with all of it now because you don't need it. It's not useful. I'm just going to go over some of the useful ones. To highlight on the symbol side of things, this is the number of symbols that can be used to indicate one type of weld, which is only one type of fixing, which is only one type of thing you might want to describe on a drawing. There's like pages and pages and pages of this stuff, most of which totally useless. And if you do need it, you look it up. That's what the internet's for, right? Okay, so 2 drawings here. We'll go to our stock standard one first, because it's nice and simple. These lines, which we've mentioned before, long, short, here, short, long, they're called center lines, and they denote the center, or probably more easily defined symmetry of an object. So this down the middle is a center line, implying that the left hand and the right hand side of this object are mirror images of each other. Okay. Whenever you put a hole in, the convention is you put 2 intersecting center lines in the middle of a hole. If ever you do this, this implies to me this object is round, and this is where the center of the circle is. They're important because if you just put a hole in something, its center has no geometry. Like there's not actually anything in space at the center of this big 32 diameter or radius 16 hole. So if you wanted to dimension to the center of it, well, you need something to tie that dimension to. Centered lines are great for that. So you can see, yeah, that's a distance to a center line. Okay, so there's center lines. This is a diameter symbol. So 2 by diameter 10, meaning 2 circles here are 10 millimeters in diameter. This is a radius, so radius 16. Anything that's going to be a hole, that's going to be a drill bit is used to make this. Drill bits are measured by diameters, so you always put diameters in. All right, don't put radiuses to this because that's just a pain in. So 2 by diameter 10. Moving on to our more complex drawing down here. This is a CAD model, obviously. We see something similar. 8 by diameter 7.9 to 8.1. This is a tolerance. So they're putting in a hole is acceptable anywhere between 7.9 or 8.1. So just get your 8 mil drill bit and drill it, is basically what that's telling me. There's 8 of them, and they're spread 1 every 45 degrees. I don't know if you actually need that, but fair enough. We see our center lines again, going to the center of this object. And you see this weird center line that goes around and intersects all of the other circles, diameter 86. This is called a pitch circle diameter, and it's basically the diameter of the circle you would scribe on this object first, so that you could place where all of these circles was going to go. But a PCD, pitch circle diameter, is what that thing's called. It doesn't come up very often, but you've heard the term Again, the use of the diameter symbol here to tell me that this thing is a view of a round object. So that's a diameter. We can see nice and clearly on this drawing as well a difference between the thicknesses of the lines. So we've got our bigger, thicker, blacker drawing lines as opposed to our center lines and our dimension lines and things like that, which are thinner. So we spoke about that earlier, right? Having a clear distinction between your drawing lines and your projection lines, or whatever you want to call them. So that's all of those. This is a thread. So like a bolt has a thread cut into it. This is a metric 42 millimeter. So that tells me that diameter of 42 millimeters metric thread. And metric threads, there's a standard. If they have a particular diameter, it tells you stuff about their shape and their size. So metric by 1.5 tells me its pitch. But that's a bunch of symbols that tell me about how this thread is meant to be cut. And that's most of the common ones. There's a few uncommon ones on here, which is perpendicular, and I think a parallel, and then a flatness, I believe, are these three. And they're three different types of tolerance, which probably not something that we're going to bother getting into now. Something that this is missing. So this is a section view, and we will talk about section views in the future in, again, 1 or 2 slides time. And it's basically telling me, imagine if you cut this thing in half, and I was showing you a cut in half section. What you would normally do is denote the cutting plane that you cut with one of these styles of line. And they haven't done it in this drawing. It's probably redundant to have done it. They probably thought it added more confusion than it saved. But just so you know, cutting plane is a different type of line. The other one, we haven't spoken about break lines. So if you've got something, and you commonly do in engineering, where you've got a long bar, one end of it's got something interesting on it, the other end's got something interesting on it, and all the middle of it's just boring crap. So you put a break line in the middle, and you can shrink the length of that bar. So you can do your 2 interesting ends, and you just put a big dimension in the middle and say, oh yeah, it was like 2 meters away. Don't worry about it though. Nothing happens in the middle. So they're break lines. I did miss hidden lines. Didn't speak about that. So hidden lines are things that basically, if you had some form of X-ray vision, you would effectively be able to see these holes that are punched in the top of this object. So they've been drawn in here basically to just tell you that this hole goes all the way through the object out the other end, that it is in fact a full hole. The reason why they're used here is that this top view itself doesn't necessarily tell you that these holes go all the way through. They could come down and just sort of end halfway. And if they did, this top view would look identical. But these hidden lines would look different. So hidden lines can be used to show that type of geometry, or a section can be used. So, views. Kind of meandered into here a little bit already, but I'm going to do this. I'm going to slow down a little bit and do it a little bit more correctly. So you just heard me using the terms front, top, and side. That they're bad terms to be using. And a lot of people were taught through high school coming through or whatever, you get an object, you draw a front view, a top view, and a side view. It's just totally the wrong logic to have, okay? So, for one, the top may not always make sense as a top. So, our running example has been a bracket, little bracket object, that could get fixed in literally any orientation you wanted, right? So the concept of its top changes based on its application. And so labeling your views becomes highly misleading, and you should almost never do it. The image that you're actually looking at here is the only example I've ever found in it so far that I've ever used where labeling a view would be important. The reason being, this thing's a jack, and a bottom does make sense for this object. But in general, don't label your views. It's the wrong thing to do. The other thing that's the wrong thing to do is putting a front, top, and a side view on and going, that's the correct number of views, job's done. It's totally not. So in some cases it might be, but sometimes you'll need less, and here we only needed 2 views. Sometimes you'll need more. Sometimes you'll need 8 views. Whatever, that you need as many as you need, and you don't ever use a redundant view. Okay, so don't just blindly make 3 views and dust your hands and assume it's done. You draw as many as you need to. And you never need to label them, because the way you lay them out on your page, which we'll talk about on the next slide, tells me what type of view they are. These views, the term that we use is orthogonal views, or orthographic projection. So if anybody throws a big word at you that you don't know that sounds funny and starts with O, they're probably talking about this type of view. They're perfectly perpendicular views of an object. Their main purpose is they're really good for manufacturing. So when you're building an object, having this type of view is super useful, because you can then put your ruler on things and measure stuff up. It's the most useful way to do it. It's not always the most obvious representation of what an object looks like, though. For that, we'd normally use some form of pictorial view. So a 3D view in some way, shape, or form. The most common in engineering by a mile is isometric, and it's really the only one that's worth knowing, but there are others. This is an isometric view. Isometric is good because it ISO 1 metric measurement, meaning this object, you could put your ruler on any one of these vertical lines, or any one of those lines, or those lines, and measure it, and it would be correct. So you draw everything to the same ratios. Again, really good for engineering applications where exact dimensional accuracy is important. It doesn't give the most realistic view of an object, though. It doesn't look quite right to do proper isometric views of things, because as we know, as things are further away from us, they are smaller. So a perspective view does that. It makes parts that are further away from you, so that line isn't as long as that line. It makes things look more realistic, more like a photograph, but less useful if do you actually know, is this thing shrinking, or is it just the perspective? You can't measure things anywhere near as easily on a perspective view. It's for architects, is what it's for. Looks better, doesn't communicate as much information. It's for architects. Oblique views are interesting. What you do with an oblique view is you draw the front face perfect, square, as though you were directly facing it, and then you skew your other dimensions out. So if you make your other dimensions come out at a 45-degree angle and be half as long as normal, they kind of look roughly right, but then you lose all this accuracy on the sides. There is a use for it, and it's literally making cabinets. It's furniture making. So often with furniture making, your front face is really important, and you want to make a really, really good view of that. And then the rest of it's like, and then the table continues, or the cabinet continues, and then it stops, and it's plain. So if you're making furniture, go nuts with an oblique view. If you're an architect, go nuts on perspective. If you're an engineer, use an isometric view. If you want to learn how to do isometric sketching, it can be done. It's a little bit more challenging. You probably want to get yourself some isometric grid paper to start, and Google it. There's hundreds of people out there who will teach you how to do it. Okay, so they're your 2 main types of views. Now these are kind of subsets of views that we'll talk about for the rest of this slide. Section views, which we've already spoken about fairly extensively. So if you imagined you got your object and you cut through the middle of it and then you wanted to look at it, that's what a section view is. So this is a section view of the camera. So that's what happened here. They put in one view and then they put in a sectioned view of the side of this object. It's really great for showing internal geometry. I can see that there's a hole drilled up the center here and da-da-da-da. So anything that's a cut face, so this is a cut face, that's been cut in half. All of this has been cut in half. Anywhere you've cut gets these hatching. Anywhere you haven't cut, like in there, doesn't. So it would just be a normal surface that you'd look at, and it doesn't get the hatching. So section view is fantastic for showing internal geometry. There's an argument to be made here that if you were ever to use a hidden line, you should have just used a section view instead, because they're better in every way. They take longer to draw, but they're very, very good. Another option that's really useful is an assembly view. So it's several isolated parts that have been stacked together. This is an assembly view. This is an exploded assembly view. So an assembly, but you can sort of see how these parts have been pulled apart and would fit back together. The exploded assembly views are IKEA drawings, right? That's exactly what they are. So it's just all of the parts that you have kind of coming together. Fantastic for instructions and stuff like that. And then we get a detailed view. So we've got a piston here. It's got a quarter section taken out of it. It's got an orthographic projection here. And then as a subset of that, it's got a detailed. So pretty simple, detailed view. Part of that just made bigger so that it's easier to work with and easier to see. And you can also see from our running examples that these things aren't used in isolation. They're almost always used in combination. So isometric view plus section plus detailed plus orthographic all on the same page. And then auxiliary views. And this is getting a little out of where I would expect you to be, but if you've got a weird, funky object and it's got some surfaces on it that aren't well represented by an immediate sort of 90-degree angle view, you can put in other views that basically effectively directly face this particular front on. And then you can dimension things with higher accuracy. So a whole bunch of different tools at your disposal. You use the ones that are appropriate. It might be appropriate, as we see here, 1, 2, 3, 4, 5 different views in this particular example. This one has 3 views, but it's using all these different techniques in combination to do the best conveying of information that it can. And this is why often you make lots and lots of sketches. Because you started this thing, you started drawing it, and you realized, oh no, I really should do a partial section, or I really want to chuck in an isometric, or no, I've ran out of space trying to draw this. What I should do is draw it smaller and then put in a detailed view. Whatever. You kind of just learn these things as you go. Okay. So yes, some planning will definitely help you, but again, sketches are cheap. So have a quick go at it, see if it works. Awesome. All right. So I just want to touch on this third angle projection. I did sort of mention that where you put your views on the page does really matter. So I think most people kind of get intrinsically when they're drawing orthographic views that sort of the way that you think about it is you take your object and you look at it square on from each different direction and you draw what you can see. So, you take an object, take the glass box is what we generally call this. Imagine there's a glass box around this object and you're just going to look at it. Okay, I can see exactly this, and take your marker and draw on your glass box effectively exactly what you can see from there. And then you get up and you look on top of it and you draw exactly what you can see. And you get on this side and you draw exactly what you can see. So that's the glass box projection. Tells you what you should draw from each thing. But where you lay them out on your page with third angle projection, effectively what you do is you take that glass box. I know it's a different image inside the box, I'm sorry. And you unfold it. So you just kind of cut it along all of its edges and you unfold your glass box. You unhinge it out. And then you unhinge it out to be flat. And then it tells you where all your views go. Okay? So it perfectly lines up these two views, right? They line up perfectly there and perfectly there. And our base lines up perfectly across here. The view from underneath is directly below this view here. So this largely is why labeling your views is a total waste of time, because where you put them on your page already tells me that. And it's totally unacceptable to take this view and just put it up here to save space or something like that. Like, that's so not okay. So yeah, this is effectively how you do it. In third angle projection, you have your glass box that you look at, and you move yourself around the object. All right? That's in total contrast to how the Americans do it, where they use first angle projection. What you do with first angle projection is you put your object like you have an object on a piece of paper, and you draw what you can see. And then the view that you put above it, up here, you rotate the object up, and then you draw what you can see. So what happens is the bottom of the object on the page appears above the front face that you drew. If we're going to hold on to this terminology, and this terminology does actually help with the teaching. Front face, bottom face is above it, and the top face is below it. And that, to me, is just dumb as a thing. Anyway, Americans. So, that's first and third angle projection. We use third. Third's most common, but most of the engineering software packages I've encountered in my life were all made in America, so by default, most of them set themselves to first angle. As a formatting rule, though, where you put your drawings on your page implies a huge amount of information. Cool. Title blocks. So this is the last thing that I want to talk about to put onto your drawings. I wouldn't expect you to hack out a hand sketch and put this thing, it's called a title box, a title block, depending on who you talk to. Generally sits in the bottom right-hand corner of the page, generally sits down here, and contains a huge amount of information. Now, I wouldn't say you should be drawing them, but the reason I want to bring them up is they're effectively a really good checklist for you to think through and go, have I addressed da 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 da. So, you don't always need one, it's a good checklist. So things that are almost always in a title block. Does it have a name? And then does it have a revision number, date, checker, contractor? So have you done your admin properly here? How many versions of this drawing do you have? How many iterations of your design are you up to? You're up to design 16, version 3. You Tony Starking this with Mark 47 armor. Which thing is this drawing for, right? So have you done that? Can be really, really useful. Again, seems trivial when you start, but ends up being super useful by the end. Sheet number's the other one. So right down here it says sheet. If we go back really quickly to now this example, this has a sheet number in it. That's sheet 4 of 4. So if I look at this, it's an assembly, right? And what it probably has is a drawing for that part, a drawing for that part, a drawing for that part, and then this is an assembly for all of them. So it can be really useful to label how many different drawings you're supposed to have so you know if you're missing one, effectively. You can also put in a title block global tolerances, surface finishes. So what can be really useful is to say, in general, a plus or minus 1 millimeter tolerance is fine on everything in this object, apart from that one place where I've specified it that I need it to be really, really, really accurate. Okay, so global tolerances and surface finishes, which are generally quite coarse, are nice things to put on your drawings. But again, it's just, have you thought about it? Do you know what you consider to be acceptable here? Also, units, again, lots of communication with other places. Are these inches or are these millimeters? By the way, they're basically the only two acceptable units. Centimeters is not an acceptable unit on a drawing. You are only ever millimeters, inches, or sometimes at the huge scale, meters. But that's it, okay? What material are these things being made out of, and how many do you need? Again, small projects, this will seem obvious to you and you won't bother writing it down, but once you've got a few hundred parts that are coming together and you've got some brackets that are steel and some brackets that are aluminium, like, oh, which ones are these again? Oh no, I just made 5 out of the wrong damn material. I have to go back and restart. Write this stuff on your drawing. A scale is always included on a good drawing as well. This would be one of the ones that kind of changes. With a hand sketch, I wouldn't stress too much about your scale, but if you actually make a proper CAD model and then a drawing, you should always include a scale. Cool. So I'll do the recap of that, and then the end of this video is just a really quick chat about schematic models for a while. But to recap everything that we've learned about our text sketching, you now have another tool in your communication arsenal. You want to communicate something to somebody, you've now got another thing that you can whip out and go, bam, you know what, I'm going to draw it, which is cool. We want to be really conscious when we're communicating this, that what's important and what isn't. A kind of straight line communicates just as much information as a measured ruled line, okay? And a kind of straight line with a dimension on it is just as good. Your job is to communicate, not to waste time. There is a whole bunch of A standards. So AS 1100, by the way, if you're interested, is the drawing standard to which we do everything. Whole bunch of standards that tell us about all these different lines and symbols and things that we can use as formatting to help us communicate. And we understand that our reader is going to make a bunch of assumptions that is going to help us communicate as well. Cool. Oh, too far. And the other one is to not use these things totally in isolation. So this is kind of the extension of that title block. You can put information on it to help somebody understand your drawing. You can also just write notes to go with your drawing. Here's my 4 drawings together, and here's a 1-pager explanation that I would hand to somebody going, all right, I'm trying to make a thing that does this. This part's to do blah, this part's to do blah. I really care about this, and I don't give a crap about these other things. Use, as we always do, our communication methods together so you can synergize them to get a better outcome. All right, so don't just think, oh, like a drawing can be standalone, but it doesn't have to be, and in general it should be. Cool. So there you go. That's a new tool for you. For those of you who are still interested and still with me, another type of drawing, not exclusively engineering drawing, but a really useful one, is schematic diagrams. So these are probably been encountered by anybody who's gone on a good public transport system, where you see things like subway lines and train maps and whatnot marked out in a way that looks like this. And this isn't how they're obviously realistically portrayed. This is how in the real world they're actually laid out. But there's a whole bunch of things that you're going to want to communicate to somebody in your life, or they're going to want to communicate to you, that the physical distance between objects is nowhere near as important as the connections between them. And that is effectively where schematics come into their own to become really useful. So for example, a subway map often will have a whole bunch of detail in the middle with loads and loads of connections in it that are really important, and you want to draw them big and obvious and easy. And then it'll have other things. Yeah, great. That's good. You get to sit on that train for a really long time. No one cares. So instead of letting these couple of offshoots take up most of our drawing, and then our really important area gets squashed, we just do away with how far away physical things really are, and we just draw the connections. And thus the schematic diagram emerges. Okay. They drew subway maps like this for a really long time before somebody figured out that it was redundant and you could do this and it was better for everybody. Into engineering, here is your circuit diagram, right? That's schematics 101. Circuit diagrams are by far the most commonplace. I would expect most of you to see them. They make use of the fact that electricity moves real fast, and so it doesn't really matter how long you make one of these distances. So also the other thing that you'll notice on this and most schematic diagrams, in fact, is highly symbolic, or the information is highly conveyed using symbols. So this is a symbol for a resistor, for example. This is a symbol for a capacitor. You got diodes and inductors and voltage supplies and speakers and whatnot. Highly symbolic representations. Again, this resistor isn't physically necessarily the same size as that resistor, but it doesn't matter in this case. Not just limited to electrical though. This is some form of processing facility, conveyor belts, blowers, trucks, forklifts, hoppers, bins, rotary dryers. Again, highly symbolic, irrespective of distances between objects. They're drawn where they are convenient, not where they may necessarily be in reality. And another processing. So this is more like a chemical processing facility. It's combustion. So it's the combustion of a gas process. But this is applicable to anything in the chemical or renewable or whatever sectors where you've got some form of reaction going on. Same deal. Highly symbolic. Actual physical layout's not mattering. And finally, this one's hydraulic systems, right? So fluid power, this is a hydraulic clutch system. So they permeate through a large number of different engineering disciplines, and they're one of those ways where, if you remember back many, many weeks ago, I actually talked about bow diagrams, and we saw schematic views of mechanical, electrical, chemical systems all interacting with each other. So they're a way of communicating between different engineering disciplines. Cool. That's it. That was just a light touch on that. So I hope you learned something interesting out of this video. I'll keep chucking up bonus content. Gain as much as you can from it. I hope it can keep you interested whilst you're in your quarantine facilities. Cool. Thanks, everybody. No.